There are two kinds of ways of looking at mathematics, which for the purpose of this lecture I will call the Babylonian tradition and the Greek tradition. In Babylonian schools in mathematics, the student would learn something by doing a large number of examples until he caught on to the general rule. Also, a large amount of geometry, for example, was known. A lot of properties of circles, theorem of Pythagoras, for example, formulas for the areas of cubes and triangles and everything else. And some degree of argument was available to go from one thing to another. Tables of numerical quantities were available so that you could solve elaborate equations and so on. Everything was prepared for calculating things out. But Euclid discovered that there was a way in which all of the theorems of geometry could be ordered from a set of axioms that were particularly simple. And you're all familiar with that much geometry, I'm sure. But the Babylonian attitude was, if I make my way of talking what I call Babylonian mathematics, is that you know all these various theorems and many of the connections in between, but you've never really realized that it could all come up from a bunch of axioms. Modern mathematics, the most modern mathematics, concentrates on axioms and demonstrations within a very definite framework of conventions of what's acceptable and not acceptable as axioms. For example, in geometry, to take something like Euclid's axioms modified to be made more perfect and then to show the deduction of the system. For instance, it would not be expected that a theorem like Pythagoras' is that the sum of the squares of the areas of squares put on the sides of the triangle will equal the area of a square on a hypotenuse should be an axiom. On the other hand, from another point of view of geometry, that of Descartes, the Pythagorean theorem is an axiom. So the first thing we have to worry about is that even in mathematics, you can start in different places. Because of all these various theorems are interconnected by reasoning, there isn't any real way to say, well, these on the bottom here are the bottom, and these are connected through logic. Because if you were told this one instead, or this one, you could also run the logic the other way if you weren't told that one, and work out that one. It's like a bridge with lots of members, and it's over-connected. If pieces have dropped out, you can reconnect it another way. The mathematical tradition of today is to start with some particular ones which are chosen by some kind of convention to be axioms and then to build up the structure from there. The Babylonian thing that I'm talking about, which I don't really not Babylonian, but it's to say, well, I happen to know this and I happen to know that and maybe I know that, and I work everything out from there. And tomorrow I forgot that this was true, but I remembered that this was true, and then I reconstruct it again, and so on. I'm never quite sure of where I'm supposed to begin and where I'm supposed to end. I just remember enough all the time so that as the memory fades and the pieces fall out, I put the thing back together again every day. The method of starting from the axioms is not efficient in obtaining the theorems. In working something out in geometry, you're not very efficient if each time you have to start back at the axioms. But if you have to remember a few things in the geometry, you can always get somewhere else. It's much more efficient to do it the other way. And what the best axioms are not exactly the same, in fact, are not ever the same, as the most efficient way of getting around in the